Welcome! In this session, we will explore LeetCode problem number 2112, titled Insufficient Data in Training to Fetch Exact Title. While the exact problem details are unavailable, we will hypothesize various efficient approaches to solve it. Let's dive in and see what strategies we can employ to tackle this problem. In this problem, labeled as LeetCode problem number 2112, we are tasked with solving a computational challenge. However, due to limitations in the training data, the exact title and detailed description of the problem are unavailable. While this makes it challenging to provide a comprehensive overview here, you can find the full details, including the problem statement, on the official LeetCode page linked in the slide. Unfortunately, the input and output formats for the problem are also not provided, which means we don't have specific examples to demonstrate how the function or algorithm should behave. For now, let's consider the placeholders shown in the example, where the input is represented as an empty list, and the expected output is noted as none. These examples are incomplete but serve as a starting point for understanding the structure. Since detailed examples are not available due to the insufficient data issue, we see another placeholder example where the input is again represented as an empty list, and the output is noted as none. This reinforces the fact that without complete data, we are unable to analyze specific cases or derive patterns. Similarly, no constraints are provided for this problem, which would normally help define the boundaries or limitations of the input. To proceed further, you will need to refer to the official problem link for the complete problem statement, including any missing details like input, output formats, and constraints. This will give you the context necessary to begin solving the challenge effectively. When tackling algorithmic challenges, there are several approaches we can consider, starting with the brute force method. The intuition behind brute force is straightforward. It systematically explores all possible configurations or solutions to the problem. This is often the go-to strategy when first encountering a new or complex problem because it provides a clear baseline for correctness. For example, if the problem involves arrays, brute force might involve nested loops to examine all pairs or combinations of elements. Similarly, in graph problems, it could involve exhaustive depth-first or breadth-first searches without additional optimization. However, brute force comes at a cost. It is computationally expensive, with time complexities often reaching n squared, n cubed, or worse. While this method is easy to implement and understand, it becomes impractical for larger input sizes due to its inefficiency. This is why we need to eventually pivot to more optimized approaches. Optimized solutions build on the brute force approach by leveraging patterns or properties in the problem to reduce unnecessary computations. For instance, sorting the input might allow us to apply binary search or two-pointer techniques, significantly improving efficiency. Hash maps and sets are also commonly used to enable constant-time lookups, while dynamic programming helps break larger problems into overlapping subproblems that can be solved more efficiently. Implementation here often involves more advanced data structures like heaps, tries, or segment trees, and the goal is to reduce time complexity to n log n, or even n, where possible. While these methods demand deeper insights and are harder to implement than brute force, they are crucial for handling larger inputs effectively. Beyond these, alternative strategies such as divide and conquer, greedy algorithms, or backtracking offer tailored solutions for specific types of problems. For example, divide and conquer can split a problem into smaller, independent subproblems, while greedy algorithms focus on making locally optimal choices to achieve a global solution. Each of these strategies comes with its own trade-offs, making it important to assess their suitability based on the problem's nature. For this problem, we adopt the optimized solution as our chosen strategy. The key intuition here is to balance efficiency with complexity by analyzing the problem's constraints and properties to avoid redundant computations while maintaining correctness. Success in this approach often hinges on recognizing patterns, such as monotonicity, symmetry, or overlapping subproblems, which can simplify our solution. For example, sorting the input might reveal opportunities to use binary search or sliding window techniques effectively. This approach is preferred because brute force, while simple, becomes infeasible for large-scale inputs, and other alternatives, like divide and conquer or greedy methods, may not guarantee correctness in all scenarios. The optimized solution strikes a balance. It is efficient, reliable, and scalable, making it suitable for larger datasets. By combining problem-specific insights with advanced techniques, we ensure that the solution is not only correct but also computationally manageable, achieving the best of both worlds. Here, we start by addressing the assumptions for solving problem number 2112. Even though the exact details of the problem are unavailable, we can hypothesize that it revolves around identifying and addressing inefficiencies in a dataset or computational process. To tackle such a problem effectively, the first step is understanding the problem requirements. This involves identifying the type of input data, such as an array, tree, graph, or string, and determining the desired output, whether it's a numerical value, a transformed data structure, or a Boolean result. Constraints like the size of the input or handling edge cases, such as empty datasets, must also be clarified. After this, selecting the right data structures becomes critical to optimize efficiency. For instance, arrays are ideal for indexed access, hash maps are excellent for quick lookups, stacks and queues are useful for sequential processing, and heaps are great for priority-based operations. Making these choices early ensures that the foundation of your solution is solid. Now that we have a clear understanding of the problem and the right data structures, we move on to designing the algorithm. The first step is input validation. This involves checking for edge cases, such as empty inputs or null values, and returning early for invalid inputs to save computation. Next, we pre-process the data if needed. For example, sorting an array can simplify operations like binary search or two-pointer techniques. The core logic comes next, where you traverse or manipulate the data based on the problem's requirements. This might involve loops, recursion, or divide and conquer strategies. For instance, if the task is to find duplicate values, you can iterate through the data while maintaining a hash map to track scene elements. Finally, the output construction step transforms intermediate results into the desired format, such as a list, integer, or string. This systematic design ensures that the algorithm is both efficient and easy to follow. With the algorithm designed, the next step is optimization. Start by analyzing the time complexity of each step. For example, sorting typically takes O(n) log n, while simple traversal takes O(n). Look for opportunities to minimize redundant operations, such as replacing nested loops with hash maps for O(1) lookups. Additionally, consider optimizing space usage where applicable. For instance, in-place modification can be used if the problem allows modifying the input structure to save memory. Once the algorithm is optimized, it's essential to test and validate it thoroughly. Use a variety of inputs, including small and large datasets, as well as edge cases like empty inputs or extreme values. Comparing the outputs against expected results ensures the algorithm's correctness and robustness. To solve problems efficiently, there are key insights to keep in mind. First, the choice of data structures is vital. For example, hash maps can reduce lookup time from O(n) to O(1) compared to lists. Divide and conquer techniques are another powerful tool. By breaking the problem into smaller subproblems, you can simplify logic and improve efficiency, as seen in algorithms like mergesort, which achieves O(n) log n complexity. The two-pointer technique is particularly useful for optimizing searches in sorted arrays, reducing complexity from O(n) squared to O(n). Additionally, dynamic programming is effective for problems with overlapping subproblems, where memoization avoids redundant calculations. Finally, handling edge cases early in the process prevents unnecessary computation and runtime errors, ensuring that your solution is both efficient and reliable. Let's take a closer look at some common data structures and their use cases. Hash maps are excellent for O(1) lookups, making them ideal for tasks like finding duplicates or counting frequencies. Arrays are a go-to choice for indexed access and efficient storage. For example, they're great for storing and sorting elements. Heaps are perfect for priority-based operations, such as finding the kth largest or smallest element in a dataset. Trees and graphs are invaluable when working with hierarchical or connected data. Use cases like depth-first search or breadth-first search rely heavily on these structures. Understanding the strengths of each data structure allows you to select the most appropriate one for the problem at hand, ensuring that your solution is both efficient and elegant. To bring it all together, consider an example problem where the goal is to find the longest increasing subsequence in an array. A naive approach would involve generating all possible subsequences and checking each one for increasing order, but this results in an exponential time complexity of O(2 to the power of n). An optimized solution leverages dynamic programming. Here, you maintain a DP array where DP I stores the length of the longest increasing subsequence ending at index I. This reduces the complexity to O(n squared). Further optimization can be achieved by incorporating binary search, bringing the complexity down to O(n log n). Key operations in this process include traversal, where you loop through the data, condition checks, to compare elements or states, updates, to modify or store intermediate results, and output transformation, to convert these results into the desired format. By following a structured approach, you can break down and solve complex algorithmic problems efficiently. This Python implementation provides a placeholder solution for LeetCode problem number 2112. Since the exact problem description is unavailable, the code assumes a general structure where the input is a dataset that needs processing and validation. The solve function accepts the input data and initializes an empty result list. It iterates through each item in the dataset, checks if the item is valid using the is_valid helper function, and processes it using the process helper function if valid. The processed items are appended to the result list, which is returned at the end. The is_valid function currently assumes all items are valid, and the process function performs no transformation, returning the item as is. This structure can be modified to include specific logic as per the actual problem requirements. Here, we begin by importing the necessary Java utilities and defining our solution class. Inside this class, we implement the main method, solve, which takes a list of strings as input. The first step is to handle edge cases where the input data might be null or empty. If that's the case, we return an empty list immediately to avoid any errors or unnecessary processing. Next, we initialize a result list to store the processed output. We then iterate through each item in the input list, using a helper method called isValid to check if the current item meets certain criteria. If it does, we process the item using another helper method, process, and add the result to our output list. For now, both helper methods serve as placeholders, allowing us to focus on the structure of the program. In this part, we define the process method, which is responsible for transforming the input item into its final form. Currently, the method is a simple placeholder that returns the item as is, without applying any transformations. This setup provides a clear and modular structure, making it easier to extend or modify the logic later. By separating validation and processing into their own methods, the code remains clean and readable, allowing us to focus on specific tasks within the implementation. This modular approach is a key principle in Java programming and helps maintain scalability and flexibility as requirements evolve. Here, we begin with an edge case where the input list is empty. The solve method is called with data set to an empty list. The function first performs an initial check to see if the input is empty using the condition if not data. Since the condition evaluates to true, the function immediately returns an empty list. This is a simple yet critical step, as it efficiently handles the edge case without unnecessary computation. By directly returning an empty list, the function ensures that it behaves predictably when no data is provided. This approach not only saves processing time but also prevents potential errors down the line. Now, we examine a case where the input contains valid data but does not require any transformation. The solve method is called with the list 1, 2, 3. As the input is not empty, the function initializes an empty list called result to store processed items. It then iterates over the input list, validating and processing each item. For the first item, 1, the is_valid method confirms that it is valid, and the process method returns it unchanged. This is appended to the result list. The same steps are repeated for the second item, 2, and the third item, 3, both of which are valid and added to the result without modification. Once all items are processed, the function returns the result list, which remains 1, 2, 3. This shows how the function handles straightforward inputs by validating and appending items directly. In this example, there are no invalid items in the input, and the process method does not alter the data. Each item is simply validated and appended to the result list as is, resulting in the final output, 1, 2, 3. This demonstrates the base functionality of the method, where it iterates through the data efficiently and appends valid items to the result without any transformation. This behavior is useful for scenarios where the input data does not require complex processing but still needs to be validated. Next, we consider an example where the validation and processing logic are modified. The input list is 1, -2, 3, and the is_valid method is updated to return true only for positive numbers, while the process method doubles the value of valid items. The function begins by initializing an empty result list. For the first item, 1, the is_valid method returns true since 1 is positive. The process method then doubles it, resulting in 2, which is added to result. The second item, -2, is negative, so is_valid returns false, and the item is skipped. Finally, for the third item, 3, the is_valid method confirms it is valid, and the process method doubles it to 6, adding it to the result. After processing all items, the function returns the list 2, 6, showcasing how the modified logic filters and transforms the data. This case highlights the function's adaptability when the validation and processing rules are adjusted. By filtering out negative numbers and doubling the positive ones, the function demonstrates its ability to handle more complex data requirements. The modifications to is_valid and process allow it to tailor the output to meet specific conditions, such as excluding certain values or applying transformations. This flexibility makes the function robust and suitable for a wide range of use cases, from simple validation to more advanced data processing tasks. In this solution, we evaluate the time complexity step by step. First, the for loop is responsible for iterating over each element in the input data. If the size of data is represented by n, this iteration contributes O(n) to the time complexity. Next, we have the is_valid method, which is called once per element during the iteration. Since the placeholder implementation of is_valid always runs in constant time, or O(1), the total contribution of this step is O(n) O(1) equals O(n). Similarly, the process method is invoked once for each valid element. Its placeholder implementation also operates in O(1), so the contribution here is again O(n) O(1) equals O(n). When we combine all these steps, the overall time complexity for the solve method becomes the sum of these contributions, which will simplify further. Adding up the contributions, we get O(n) plus O(n) plus O(n), which simplifies to O(n). Now, let's analyze the space complexity. First, the input data is directly provided and does not consume additional memory. Next, the result list is used to store processed elements. In the scenario where all elements are valid, the result list will contain all n elements, requiring O(n) space. For auxiliary variables like item inside the loop, memory usage is constant and does not scale with input size, contributing O(1). Additionally, since no recursion or deep call stack is involved, there is no additional memory overhead from stack space, which also contributes O(1). Combining these components, the overall space complexity is dominated by the result list, and we'll summarize it shortly. The total space complexity is O(n) for the result list plus O(1) for auxiliary variables, which simplifies to O(n). Now, let's compare different cases. In the best case, where data is empty, no iteration occurs, and the method directly returns an empty list. Here, both time and space complexity are O(1). In the average and worst cases, where all elements are valid, time complexity is O(n) due to the single traversal, and space complexity is also O(n) because the result list stores all elements. Compared to a brute force approach that might involve nested loops or redundant operations, which could escalate complexity to O(n)² or higher, this implementation is far more efficient. The single traversal and constant time validation make it optimal for linear processing tasks. Finally, the dominant term analysis confirms that both time and space complexity scale linearly with the size of the input, validating the O(n) efficiency for this solution. When tackling problems, it's essential to be mindful of common mistakes that can derail your progress. First, misinterpreting the problem statement is a frequent issue. This often happens when edge cases or constraints like empty inputs or maximum input sizes are overlooked. It's common to rush into implementation without fully understanding the requirements, but you can avoid this by taking the time to write down examples, including simple and edge cases, to validate your understanding before you start coding. Next, an inefficient algorithm choice can lead to suboptimal solutions. For instance, you might use a brute force approach with O, n superscript 2, complexity when a more efficient algorithm, like one with O, n log n, is available. This usually occurs due to a lack of familiarity with optimal algorithms for the problem type, such as dynamic programming or divide and conquer. To avoid this, evaluate the problem constraints carefully and think critically about the most efficient approach. Another common pitfall is incorrect index handling, which can lead to off-by-one errors or accessing out-of-bound elements. These mistakes often arise due to confusion between zero-based and one-based indexing or neglecting to validate indices. To mitigate this, use clear variable names and explicitly check edge cases that involve indices to ensure correctness. Another frequent oversight is failing to optimize space complexity. This happens when unnecessary auxiliary data structures are used, or in-place solutions are not explored. Often, we focus solely on time complexity and overlook the importance of efficient space usage. To address this, once you've implemented a solution, take a step back to review it for possible space optimizations. Additionally, skipping edge cases during testing is a significant mistake. Examples of this include neglecting empty inputs, failing to consider minimum or maximum constraints, or overlooking scenarios with duplicate values. This usually stems from overconfidence in the solution or incomplete test coverage. To prevent this, develop a checklist of common edge cases and ensure you validate your solution against them. This approach not only increases the robustness of your solution but also prepares you for scenarios that might otherwise slip through the cracks. Beyond avoiding mistakes, there are strategies you can adopt to excel in interviews. Thinking out loud is a key technique. Articulate your thought process as you solve the problem to demonstrate your reasoning and problem-solving skills to the interviewer. Recognizing patterns is another valuable skill, as many algorithmic problems share common themes like sliding window, binary search, or dynamic programming. Identifying these patterns can help you arrive at solutions more quickly. Additionally, discussing trade-offs between different approaches, such as time versus space complexity, showcases a deeper understanding of the problem. Structured problem solving is also crucial. Begin with a naive solution and refine it iteratively. Interviewers value this methodical approach as it demonstrates your ability to improve and optimize solutions. Lastly, take the time to thoroughly analyze the problem and design your solution before writing any code. A well-thought-out plan minimizes errors during implementation and ensures a more efficient workflow. To strengthen your understanding, it's helpful to explore related problems. For instance, LeetCode number 1, 2 sum, focuses on hash maps for efficient lookups. LeetCode number 42, trapping rainwater, highlights the two-pointer technique. LeetCode number 121, best time to buy and sell stock, emphasizes pattern recognition for optimal subarray problems. Finally, LeetCode number 322, coin change, is a classic example of a dynamic programming challenge. In terms of approaches, brute force is often a starting point. While it's useful for validating correctness, it's inefficient for large inputs due to its poor performance. Optimized iterative methods, on the other hand, leverage precomputation or efficient data structures, such as hash maps or priority queues, offering significantly better performance at the cost of a slightly more complex implementation. Recursive solutions with memoization are another option, particularly for problems with overlapping subproblems. While intuitive, they require careful memory management. Finally, divide and conquer approaches are well suited for problems that can be naturally split into subproblems, though recursion depth can become a concern for larger inputs. Understanding the trade-offs of each approach will help you choose the most effective solution for a given problem. Great job! We've explored different ways to tackle LeetCode problem number 2112 despite limited information. Remember, adaptability and structured thinking are vital when solving coding challenges. Thanks for watching. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!